Welcome to video 6.4 in our first Principles of Astrophotography series. In this video we discuss the pixel scale and show how to calculate it.
The pixel scale allows you to calculate how many pixels on the sensor are devoted to a particular area of sky.
This video is based on section 6.4 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 100, pixel scale. The pixel scale, little p, of a telescope camera combination gives the angle in the sky in arcseconds that is imaged by each pixel on the camera sensor. The smaller the pixel scale, the greater the magnification and detail.
So we got a sensor. It's divided up in little pixels, and this particular pixel right here, we want to know, we got a lens or a mirror or something in between here, we want to know how much sky is imaged by that pixel, and that's what the pixel scale measures. The angle measured in arcseconds of the sky that's covered by each little pixel on the sensor. Very important. This is an image of a star that I took from one of our photographs. The white lines, here, 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 and here, divide up are showing the actual pixels in the image. And the size of the piece of sky that's imaged by that central pixel, or by any of the pixels, is given by the pixel scale, little p. Not to be confused with big P, capital P, which is the pixel size, the actual width of a pixel measured in microns. Here we're talking about how much that 3.76 micron pixel on your sensor, how much sky that sees. And that's going to depend on your optics, on the focal length, etc.
But the pixel, how much sky it sees also depends on how large the pixel is.
That's right. Yeah, so
it is dependent on the pixel sky, pixel size.
Pixel size and the focal length, and that's exactly what we will show.
Yeah. Right.
So this is a review.
Review on Principle 97, size on sensor. We talked about the linear size of the image of a celestial object on a sensor is the product of the telescope focal length and the angular size of the object in the sky.
Yeah. So that's from video 6.2 if you want to go back and review that. But D equals F theta is going to be our key to connect the size of the image on the sensor to how much angle of the sky it covers. So what we're going to do is take that D equals F lambda, or D equals F theta, and we're going to solve that for theta. We're going to divide both sides by F. So theta is going to be D over F. And then what we're going to do is we're going to say, all right, the pixel scale, that's an angle, right? Yeah, it's an angle. So we're going to replace that theta by P. It's an angle measured in arcseconds. And then we're going to say the size of the object on the sensor, we're going to just apply that to a single pixel. And the size of a single pixel is called the pixel size. Big P measured in microns, right? So little p equals big P over F. So that's exactly what we have right here. The pixel scale equals big P divided by F. So that gives the basic relationship between those three objects. And we were saying before that the pixel scale is going to depend on the pixel size and on the focal length.
Right.
And that's where this dependence comes from. And you might be saying, well, where does all this CRAP come from? And the answer is, I want to convert the pixel size to millimeters, and then I want to convert the angle that's measured in radians. I don't know if you remember, but to apply this equation, the angle has to be measured in radians. I want to convert that to arcseconds. And that's where all this gobbledygook comes from. And we go through it more carefully in the book. But I think you see basically where everything's coming from, where the basic dependencies are. So if you reduce this thing that I've drawn a big rectangle around down, you get 648 arcseconds, millimeters, divided by pi, 3.14, divided by microns. So the reason that we've written in this way is that we want the focal length to be measured in millimeters, and we want the pixel size to be measured in microns. Normally focal lengths are measured in millimeters, 250 millimeters, for example, for the C-Star S50. Pixel sizes are normally measured in microns. So if you put the focal length in millimeters, then this millimeter will cancel that millimeter. If you put the pixel size in microns, then that micron will cancel that micron. And you end up with a result in arcseconds. And so 648 divided by pi is 206.3. That's where that number comes from. So this is the pixel scale equation. When we first got started in astrophotography, I saw this equation appearing everywhere. Some people called this P the pixel scale, as we call it, S-C-A-L-E. Some people called it, confusingly, the pixel size, which is confusing with the pixel size of the sensor.
The actual sensor, yeah.
Some called it the image scale. Others called it the plate scale. And yet, I think it was in either a Gina Astro or on High Point Scientific website, they called it the, I can't remember, it was another way of describing it. Bottom line is all those different people are referring to exactly the same thing, but just using different words. So we call it a pixel scale, whatever. But I saw this equation all over the place, and I saw that 206.3, and I thought, where did the 206.3 come from? That doesn't sound like a number that I've dealt with before. It's not pi, it's not, but anyway, that's where it comes from. This derivation shows that 206.3, just plug it into your calculator. If you take 648 divided by pi, you get 206.3. So it's an approximate result. But I didn't know whether it was determined experimentally, or you could find it out theoretically or whatever, but you can find it out theoretically, and this is how you do it. Bottom line, this is the pixel scale equation, and it's very, very useful in astrophotography.
And we got pointed to that on cloudy nights? Was this?
Yeah, and I'll talk about that cloudy nights post in just a second. One reason that it's useful, well, let me do this and then we'll talk about the cloudy nights post. So, okay, so this is the same principle, just applying it to one particular telescope. So we own a William Optics Cat 91 WIFD. It has focal length of 449, roughly twice that of the C-Star S50. Our camera, so it's interesting, this pixel scale equation involves the focal length, which is related to the optics in the telescope, the pixel size, which is related to your camera, and those two play against each other in order to figure out what the pixel scale is. So you plug those two numbers into the equation, multiply, take big P divided by little f, and then multiply by 206.3. And what does that say? It says that that particular telescope with that particular camera, that each pixel in the image represents 1.73 degrees of sky, or 1.373 arcseconds of sky.
Mm-hmm. Principle 102, plate solving. Plate solving is the process of finding a match between the stars in an image and the stars in a catalog. This process yields the pixel scale, little p, of the image.
So these algorithms are completely amazing to me. How you can, like for example, astrometry.net you can take any old image, JPEG, FITS, PNG image, feed it into astronomy.net. You don't even have to tell it where it is in the sky, which hemisphere, what the size of it is, or anything. And it looks at the catalog stars and it figures out where that image was taken in the sky, what the pixel scale was.
That's crazy.
It blows my mind. And I talked to my brother, John, who's a computer scientist, and he said, oh yeah, that technology's been around for years. He said
no big deal.
It's called registration.
Okay.
You match up this image with some other image and you're registering the image.
Cool.
But I still think it's cool.
Yeah.
So this gives you the pixel scale of the image, which you can either calculate theoretically or you can get the pixel scale using plate solving, right?
Mm-hmm. All right, Principle 103, measure focal lengths. A telescope's focal length can be obtained from focal length equals 206.3, the pixel size over pixel scale, using a plate solved pixel scale, little p, and the camera pixel size, big P. Okay, so all we're doing is rearranging this equation. The pixel scale, little p, equals 206.3 times the pixel size, big P, over f. This is an idea that was introduced to me by Michael Collins in a Cloudy Nights post, and there's a reference to that discussion in Cloudy Nights in our book. But Michael posted about being able to determine the focal length from the pixel scale that you plate solved. Why is that useful? Well, because the focal length is easy for a thin lens. So the rays come in, oh, this is great. But all the rays come to the focus at the same place. You can see that. Close enough, right? Sort of, yeah.
Yeah, sort of. So they come to focus right here.
His telescope is not perfect.
Yeah, yeah. So, and that gives you the focal length, and that's how it's defined for a thin lens. But as we mentioned in the video where we talk about thin lenses, no telescope today is like that. They've got 5 lenses or 3 or 2. And where do you start measuring the focal length from? Is it from the first lens? From the second lens? Halfway between them?
Yeah.
Nobody knows.
Yeah.
And so that was a mystery to me about how you would determine the focal length. Well, Michael Collins put his finger on it. He said, take this pixel scale equation and let's multiply both sides by f and divide both sides by p, by little p. So then f's cancel here, the little p's cancel here, and you end up with f is 206.3 times the big P, the pixel size, divided by little p, the pixel scale. So he said, to find the focal length, you can look up the pixel size in anywhere online for your camera. Ours is 3.76 microns. You just have to trust whatever the manufacturer says it is. Plug that number in there. Take an image with your telescope camera combination. Plate solve the image to find the pixel scale. Plug those 2 numbers in there, and that gives you the focal length of your telescope. And I noticed that in some of our FITS images that we have plate solved, that in the FITS header, the focal length is listed. And how could it know what the focal length is? Did it go out on the internet and find out that it was a Celestron 9.25 or whatever? No, I think the plate solving software figured out what the pixel scale was. It knew, I guess it would have to know what the pixel size is, or else it wouldn't work. But I'm guessing that that's how it finds it. But anyway, that's a way you can find it if you're uncertain about what your focal length is. I know with our Celestron Edge HD 9.25 that the actual focal length that's in FITS headers differs from the advertised focal length. Not very much, but by a little bit.
This has bugged me for a long time because I've seen lenses, and even like the Cat 91 versus the Cat 108, they're almost the exact same length. And I say these should be different lengths, right?
Yeah.
The focal length is different. But it's so much is going on inside those telescopes, so we don't know about correcting aberration and all these different lenses and different thicknesses and different, whatever you call the concave cavity and convexity of them, like all of that going on, and you don't, there's no way of figuring it out straight from the telescope.
I mean, you'd have to do a horrific calculation, computer calculation, using ray tracing through all those lenses.
Yeah. But what you want is the pixel scale of your final image, so why not just use your final image and figure it out from there? But I do have a question on this. So you know how when we're out observing at night, and sometimes
at night, yeah, that's great.
At night, yeah,
that's good.
Still at night.
Oh, good.
Yeah,
yeah.
And it gets colder or warmer. The telescope expands and contracts, and our focal point kind of when we focus, that focus point is different. Does that affect our pixel scale?
Okay, that's a great question. So in the celestron, to focus, you're moving the primary mirror.
Yeah.
And so you're going to affect the focal length. And if you're affecting the focal lengths, you're going to affect the pixel scale.
So is PixInsight correcting for that when we go through and stack it?
I don't know. That's a great question. Imagine the changes are going to be really, really tiny. But given what we did with the Celestron HD, that its advertised focal length is different from the one that we're seeing.
Yeah.
I wonder how much variation. Well, maybe leave that as an exercise for the reader to figure that out. But these are the basic principles behind the pixel scale. It's extremely useful for you to, and it'll come up later when we talk about resolution. How much detail can you expect to see for a well-sampled image? It all comes back to pixel scale.
Yeah.
So,
pixel scale.
So these are, in the book we list 8 different telescopes in a table in the introduction, and can't remember which one's A, which one's B, which one's C, etc. But this is just a plot of pixel scales for those different telescopes. So you can see that some of these pixel scales for the more wide field telescopes cover 2 or 3 arcseconds per pixel. So they're capturing a lot of sky with each pixel. Whereas for high magnifications, I think this is the Celestron with a Barlow lens to send the focal length way out the wazoo. Then the pixel scale is very, very small, and you're only just seeing a tiny fraction of an arcsecond of sky with each pixel. What's good about that is it has a potential of giving you a lot of sharp detail in the sky. What's bad about that is it's hard to guide with long focal lengths, and the sky is probably not going to be perfectly transparent. And
they're probably using lucky imaging or something.
Lucky imaging, yeah, exactly. And we will talk about lucky imaging in a subsequent video too.
Yeah. Great. Principle 104: convert pixels to angles. The equation theta equals pn relates to the angular width theta of an object in the sky to the pixel scale p and the width n of the object in pixels on the sensor.
So this is kind of a no-brainer, really, at the end of the day. If p measures the number of arcseconds per pixel, then if you multiply p, that's this bad boy right here, by the number of pixels, then the pixels cancel and you get
Oh,
the angle on the sky. That's all there
cool.
is to it.
Nice.
Yeah, so this is just saying what you would have just done the calculation. You just multiply by the number of pixels to find the arcseconds. So for example, for the Cat 91 ASI 6200 combination, again, for a pixel scale, you've got to specify the telescope and you got to specify the camera. We calculated this before. The pixel scale of that combination is 1.73 arcseconds per pixel. The angular width of the Crab Nebula is about 420 arcseconds. And if you want to know how many pixels across that Crab Nebula is going to be, so we know that the angle across it from end to end is 420 arcseconds. And then the number of pixels you get across there is 243. So that's not a whole lot of pixels.
No, it's not. Yeah.
And so, I mean, in thinking about what you want to use to shoot the Crab Nebula, if you have a telescope with a longer focal length,
Yeah.
then the pixel scale equation is 206.3 times P over F. If you increase that focal length, then you're going to decrease the pixel scale, get a finer view on that object, which is basically what we're talking about with magnification. Get more pixels on
More
target.
pixels.
More pixels on target. Thanks so much for watching.
And we'll see you next time.